Okay, let's just dive right in. At the very heart of modern physics, there's this huge challenge, right?
Right.
How do we actually bring together Einstein's picture of gravity, general relativity, the big stuff, planets, galaxies with the quantum world?
Yeah, quantum mechanics.
Hmm.
The super small, the weird stuff, particles, forces.
Exactly. And they just don't. They don't play nicely together usually. You try and force them, and the math just sort of explodes. Infinities everywhere.
It really does. And finding that unified theory, quantum gravity, something that works for everything, from the tiniest quantum jitter to the whole universe curving, that's been the dream for physicists for decades.
You hear about string theory, loop quantum gravity.
All sorts of approaches. But finding one that's, consistent and avoids those infinities without complicated fixes and actually connects to stuff we can measure, that's been incredibly tough.
And that is exactly what we're getting into today. We're doing a deep dive into this one research paper. It's called Integrating General Relativity with the Quantum Vacuum by Riccardo Storti. And it offers a pretty different angle on this.
Yeah, a novel approach.
So our mission here is to really unpack this. What's the core idea? How does it use the quantum vacuum, of all things? How does it link the tiny scales to the cosmic ones? And, why does it maybe stand out from those other big theories?
And it leads to some pretty surprising places. We'll see how it actually pulls in data about protons and neutrons.
Tiny particles.
Yeah, tiny particles, to tell us something fundamental about gravity itself. And it even predicts that gravity might not be smooth, but comes in little discrete packets.
Whoa, okay. Like steps.
Kind of, yeah. Tiny steps. And it's interesting, this whole framework has even been looked at by AI systems, comparing how testable it is versus others.
Right. Okay, so settle in, everyone. We're going to explore this idea that maybe empty space, the quantum vacuum, isn't so empty after all. Maybe it holds the key.
What's really interesting, I think, is how it starts. It doesn't immediately jump to, say, extra dimensions or new exotic particles.
Okay.
Instead, it kind of subtly tweaks the equations of general relativity itself. It's like, imagine adding a sort of quantum layer or quantum information directly into how we describe space-time curvature.
So modifying Einstein's field equation.
Basically, yes.
Well,
it introduces, the technical term is a covariant time-dependent tensor operator, but think of it as injecting quantum vacuum information into GR. And this leads to a really key idea, space-time curvature, which we usually think of as smooth.
like a bent sheet.
Right. Instead, this framework suggests it can be seen as a sum of specific discrete vibrations or harmonic modes, like musical notes for space-time.
Okay, harmonic modes. But in normal quantum physics, don't you usually have like infinite possible modes or vibrations?
But that's the crucial difference here. This approach says, no, it's not infinite. There's a natural boundary, a kind of limit.
A limit to the space-time vibration.
Exactly. And they call this the quantum vacuum spectral limit, or QVSL. And the really neat part is, they argue this isn't just some mathematical convenience. It's not just assumed.
Okay.
The paper claims this limit, this boundary, is actually revealed by physical measurements we've already made. Really precise ones.
Wait, measurements of what? How do you measure a limit on space-time vibrations?
This is where it gets really interesting. It connects back to what I mentioned earlier. It links this fundamental limit to high-precision data from hadronic physics.
Hadrons, like protons and neutrons.
Exactly. Stuff like the charge radius of the proton, how big it effectively is electrically. They're incredibly precise measurements from experiments like CELEX, we're talking atometers here, tiny fractions of a fraction of a meter,
Wow.
and also the neutron's charge radius from other experiments like Kopecky and Rees. The framework basically shows how, starting from its core ideas, you can derive these incredibly precise measured sizes.
So the theory predicts the size of a proton.
Or rather, it shows that the measured size of the proton and neutron actually sets the value for this QVSL, this limit on space-time modes. It's an empirical anchor.
Hold on. So the physical size of a proton, this incredibly tiny thing, somehow dictates a fundamental limit on the vibrations of space-time itself. That seems
counterintuitive. Yeah.
It links the very small to the very fabric of space-time in a really direct way. How does that connection work? Why would a proton's size matter for space-time modes?
Well, the idea is that the quantum vacuum isn't truly empty, right? It's fizzing with these quantum fluctuations, virtual particles popping in and out. These fluctuations have energy, they have a spectrum.
Yeah.
The QVSL represents the upper limit, the highest frequency or energy part of that vacuum fluctuation spectrum that actually couples to gravity, that affects space-time curvature. And the theory then shows that the characteristic sizes of particles like protons and neutrons, which themselves emerge from complex quantum interactions within that vacuum. Well, those sizes provide the real-world data point that tells us where that spectrum cuts off.
Ah, okay. So the particle properties are like a physical manifestation of that vacuum energy limit.
That's the idea. And the big payoff is, by having this cutoff, this QVSL determined by real data, the framework naturally avoids those infinities that pop up when you try to quantize gravity in other ways.
Because you're not summing over infinite modes anymore.
Exactly. It stops the sum before it blows up. It
Uh,
effectively regularizes the theory, as physicists say, but it does it based on this physical limit derived from experiments, not through purely mathematical techniques like renormalization, which can sometimes feel a bit, well, tacked on.
right, I see. So it modifies GR, gets this QVSL limit from particle physics data, avoids infinities naturally. How does it then connect this quantum picture back to the really big stuff like cosmology? Does the QVSL apply there too?
That's another key point the paper makes. This QVSL, the same limit derived from tiny protons, seems to work across incredibly different scales.
Like how different?
The paper presents calculations suggesting the QVSL parameters are consistent not just for subatomic particles, but also for planets like Earth, and even up to supermassive black holes, like the monster TON 618.
Whoa! From protons to black holes with the same parameter.
It suggests this kind of unifying description, yeah, linking the quantum world all the way up.
And didn't you mention there was a cosmological prediction involved? Something specific?
Yes, and this is pretty striking. The paper refers back to earlier work by the same author from 2008. Using this QVSL concept, back then, that work predicted a value for the Hubble constant.
The expansion rate of the universe.
Exactly. And then 5 years later, in 2013, the Planck satellite mission released its measurement of the Hubble constant. And the measured value was, well, remarkably close to what this framework had predicted years earlier.
Okay, predicting a fundamental cosmological number years in advance based on a theory rooted in particle sizes. That's pretty compelling evidence if it holds up.
It's certainly a strong point in its favor. Making a falsifiable quantitative prediction like that, which is then borne out by observation, is quite significant in theoretical physics.
Definitely. Now, you also mentioned something about discrete gravity. What does that mean in this context?
So, if space-time curvature is described by these discrete harmonic modes, these specific vibrations, with a cutoff,
Right, the QVSL.
then the framework predicts that gravity itself, the force, or more precisely, gravitational acceleration, shouldn't be perfectly smooth and continuous. It should come in tiny, discrete steps. Quanta.
Like little packets of gravity. Instead of a smooth pull, it's like click, 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 but incredibly small clicks.
That's a good way to picture it, yeah. The paper actually calculates the predicted size of these gravitational quanta. For Earth's surface, for example, it predicts these discrete jumps in acceleration are on the order of 10 only meters per second squared.
10 to the minus 28. That's unimaginably small.
Absolutely minuscule. Different values for different objects, but always incredibly tiny. These would be gravity's fundamental units, analogous maybe to photons being the packets of light, but for acceleration.
Okay, so if gravity comes in these unbelievably tiny steps, can we actually measure that? Is that even possible?
Right now, no. Not even close. The precision needed is far beyond anything we have experimentally. Detecting a step change that small is a monumental challenge.
So it's just theoretical then?
Well, yes and no. It's currently untestable, but the paper argues it provides a concrete quantitative target for future experiments. It tells experimentalists exactly what size effect to look for, even if the technology isn't there yet. That specificity is something quite a few other quantum gravity approaches lack.
That's a fair point. Having a number to aim for, however distant. How does this whole approach, this covariant harmonic quantization, compare to the big players in quantum gravity, string theory, loop quantum gravity?
The paper directly addresses this. It draws comparisons with LQG, string theory, things like asymptotic safety, causal dynamical triangulations, CDT, group field theory, a whole range.
And the main difference, it claims, is
Empirical grounding. It really hammers this point. While other theories might have, say, elegant mathematics or sophisticated ways of dealing with infinities or describing discrete space-time,
which they do.
right, but they often struggle to connect directly to experiments we can do now or in the near future. Their predictions might involve energies far beyond the LHC or abstract concepts that are hard to test.
So this framework argues it's different because it starts with and is constrained by actual measured data, like the proton radius.
Exactly, that's the claim. It's not predicting, say, some fundamental minimum length scale that's currently impossible to probe. It shares the idea of discreteness with theories like LQG or CDT, yes. But the reason for the discreteness, those harmonic modes limited by the empirically derived QVSL, is presented as unique and directly tied to real-world particle measurements.
Okay, and that connects to the AI evaluation you mentioned earlier, how they assessed its testability.
Precisely. The paper cites results where AI platforms, DeepThink R1 and ChatGPT 4.0 apparently, were used to compare different quantum gravity frameworks on various criteria.
Criteria like?
Things like how revolutionary it might be, its scientific importance, overall value, and crucially, testability. And in that analysis, this framework, which is sometimes called the EGM construct, reportedly scored highest overall.
And particularly on testability.
Yes, significantly higher. It got something like a 9.7 out of 10 for testability. Compare that to, say, string theory around 2.0 or LQG around 3.1 on the same scale in that specific analysis.
Wow, that's a huge difference.
It is, and the AI report apparently highlighted what it called a testability crisis in the field. Lots of theoretical ideas that are just very, very hard to experimentally verify. This framework's high score was linked directly to having those empirical anchors we talked about. Particle radii matching, the Hubble constant prediction, plus that specific, albeit hard to measure, prediction of discrete gravity quanta.
Okay, so let's try and wrap this up. To summarize the main idea for everyone listening, this covariant harmonic quantization approach seems to offer a potentially different path towards that grand unification of GR and quantum mechanics, one that's deliberately tied to experiments.
That's the core message, yeah. It uses this quantum vacuum spectral limit, the QVSL, which isn't just assumed but derived from real, precise measurements on hadrons, protons, neutrons, data from SELEX, Kopecky, and Rees.
Right, the particle sizes.
And that limit naturally takes care of the infinity problems that often show up when you try to quantize gravity. It sort of self-regularizes based on physics data, not just math tricks.
And its standout feature seems to be that direct line it draws from a fundamental theoretical concept like the QVSL straight to things we can actually measure in labs, like particle properties.
Yes, and then extending that out to cosmology, making predictions like the Hubble constant one, which was later confirmed. That empirical thread runs right through it.
And then there's that bold prediction, maybe gravity isn't smooth, but comes in these tiny quantum steps around 10 resis near Earth.
Correct. A concrete number. It's a target for future tech, a clear benchmark. It sets it apart from theories whose predictions might be less specific or much further out of reach. And as we said, the AI analysis really picked up on that testability aspect, contrasting it with that wider testability crisis.
Now, it's not a completely finished picture, though. The paper acknowledges limitations.
Oh, absolutely. It's presented as a framework, still under development. They mention, for instance, that the treatment of how gravitons interact with each other, the nonlinear self-interaction of gravity, is simplified in the current state. That needs more work.
Okay.
And of course, the huge practical challenge we already discussed, actually detecting those incredibly tiny gravity quanta that's likely a long way off, requiring sensitivity leaps.
Right. So for you listening to this, the big thing to maybe mull over is, what if this is right? What if gravity does come in discrete steps, even steps as tiny as 10 ERVs? What would that actually mean for space and time at the most fundamental level?
Does it imply reality is fundamentally granular, pixelated in some way we can't yet perceive? Could we someday build instruments sensitive enough to actually see those tiny gravitational steps?
It's a pretty mind-bending possibility this research puts forward.
Definitely something to think about.
Well, thanks for joining us on this deep dive into what could be a really significant new direction in fundamental physics.